Good morning, friend. My name is T. Rajesh Kumar Dora, and today I'm going to teach you the material science and engineering. Uh, before getting into the topic, I would like to just give a brief discussion about the current situation, how it is going to helpful to the students and the faculty and parents to come out of a fear zone that has been created by the media and the people. Okay, it is very necessary for us to come out of that fear zone to a growth zone. So let's start with this chart where you can see you can consider yourself as an individual which is now present living his life during COVID situation. Assume that you are encountering these issues which was written, which has been shown in this inner ring. That means you are still in the fear zone. That, for example, assume that you are still in fear and you are frustrated and you can't able to do your day-to-day work, and you just want to overreact on certain things. So that means you are still in the fear zone. Okay, and you need to come out of the fear zone, and before getting into the growth zone you have to cross the learning zone. So what happens in the learning zone? So your situation will start a bit toward developing conditions. Okay, so that means when you start give up that you can't control things. Okay, you're telling the positivity comes around you. Okay, when you think that when you identify your emotions, okay, and you are aware of the situation and you think how to react. Okay, and you stay away from the negative things and recognize that you can do the best. That means you are slowly getting into the learning zone. And after the learning zone, okay, when you get into the growth zone, okay, you will start helping people. Okay, that is the first sign that you are into the growth zone. Okay, and you make your talent available to others. Okay, you teach people. Okay, you educate people. And then uh, when you start thinking about your present and your future, and you become more empathetic to the people. Okay, people, and you thank people for what is their for the help they're being offered. Okay, so you we will be into the growth zone from fear zone and crossing the learning zone. That is a transformation happening. Okay, and without this it is very difficult, okay, for a student to prosperous in his career. So they have to get out of this fear zone. Okay, next, before today I'll just give you a brief introduction about the material science. Okay, I will not discuss much because I think this will be a very introductory type of class where we'll be teaching something very informative, uh, not subjective kind of things. Okay, I want to make this class is a very interesting and fun. So that's why I'm not giving any heavy loaded theories and concept. Okay, maybe that can be done in next and upcoming classes. So so material science and engineering, they have been it's a hybridization of physics and engineering. So normally what happened, either people study a pure materials related things that is derived from physics, or they in engineering people read completely application oriented. But for a mechanical engineer, it is important that where they are going to apply their materials. Until unless they don't know the application of the material, it is of no use of studying material science. So that's why the course was developed. Okay, depending on the requirement of a mechanical engineer, that where he is going to use the material, especially for the design engineers. Okay, when they will be designing machine elements, they should know the application first, and they should know that uh, what are the properties they require for a particular design. So if they don't have much information about the properties of the material and where they're going to apply, it is very difficult for the design engineer to design the element. So you should know that how many types of materials are there, what are their properties, and how they are going to use. So in this way, I have tried to first give a brief introduction about the types of materials. Okay, it's nothing but your yeah your basic engineering material has been classified into metals, non-metals, and metals due to combinations. Okay, so your metals are further uh, uh, classified into ferrous and non-ferrous metals, and non-metals are being classified into ceramics and polymers. Okay, so uh, when you see the materials due to combination, you can see composite and alloy are the two sub-classification, where alloys are further classified into ferrous and non-ferrous alloys. I am going to just discuss different types of materials. These alloys and ferrous alloys, non-ferrous alloys can be discussed later briefly. Okay, in the syllabus it is there. Okay, so composites, metal matrix composite, reinforced composites, polymer matrix composites. These composites are basically used for applications where the strength to weight ratio is very important. Okay, so we have a separate section to discuss about metrics. In this subject, we will cover everything, all the things which you have mentioned in this slide. We will be going to discuss everything in the material science subject. But apart from this, I would like to throw some light on that what will be the future of material science. How okay, basic engineering materials, fine, from the academic base of, and information point of view, it is fine, but as an engineer we need to upgrade yourself to know about the future of the material. That's why I have given a small introduction about this advanced engineering materials and their classification. So you can see that advanced engineering materials are classified into your nanomaterials, smart materials, and high entropy alloys. Okay, your smart materials are further classified into shape memory alloys, piezoelectric materials, magnetostrict materials, and ER or MR fluid. ER means electrorheological, MR means magnetorheological fluid. Undoubtedly, these topics are new and it will be difficult for you to understand, but I think these are the future of the materials, and on an average these materials have started entering our lifestyle. Okay, just like for example nanomaterials. So there are so many products people are using, those are based on nanomaterials. Okay, piezoelectric materials, the sensors, magnetostrict materials, the sensor, okay, used in your mobile phones, your electronic gadgets, they are all based on these materials, these principles. Shape memory alloys. Okay, for biomedical devices, shape memory alloys have played a very important role. Okay, so for an engineering student, it is as important as to study a basic engineering materials and to study the advanced engineering materials also. Okay, so next we'll go to the classification of solids. So this is a very basic classification, that a solid, it can be classified into both amorphous and crystalline and polycrystalline material. Okay, so what is an amorphous material? You can see that amorphous material, okay, the atomic arrangement you can see in this diagram. The atomic arrangements are not regular, they are not uniform, they are randomly arranged. Okay, the classic example of an amorphous material is glass, okay, which is very fragile. The properties of glass is different than the properties of metal, because metals there is a regular arrangement of atoms. Okay, the regular arrangement of atoms which we are seeing in this case, in the case of crystalline solids, okay, is not same for all the materials. Okay, this arrangement can be different, but the necessary condition that it should be uniform. If there is uniformity is there, then you can say that it's a crystalline solid. That we will discuss in the next part, that how we can this arrangement of atoms is very important. How many ways the atoms can be arranged in a regular pattern. This all crystal sets that will come in the next session. Okay. Now coming to the polycrystalline material, there is no major difference between a polycrystalline and crystalline material, but within a polycrystalline material you will find numerous regions, okay, within which the atomic arrangements are regular. You can see this diagram where there are three regions, 1, 2, 3 regions within which the atomic arrangement is regular, but among these three regions there is a misfit. Okay, there is a small amount of misorientation there between these three regions. Okay, that is why it is called polycrystalline material. Okay, and for this reason there might be a difference in the properties of crystalline solid and a polycrystalline solid. That we'll discuss later. Okay, and you can see this gap. This gap is nothing but the misorientation, and this there is a certain terminology for this. Okay, this two the boundary. Okay, it's give a feeling of a boundary that separates these two regions. Okay, and the grain boundary concept will comes into picture and all this. So that will be discussed later. I'm just giving you a brief introduction. Okay, now this crystalline solid can further be categorized into ionic crystals, molecular crystals, network crystals, metallic crystals, polar, non-polar, H-bonded. Okay, so these things will be discussed briefly. Okay, this is the bonding between atoms. Okay, how many types of bonds are there? Everything we'll discuss. But in this lecture, I'm not going to discuss all this. Okay, I will discuss very interesting historical facts. Okay, what happens to the material science, how they evolve. Okay, so okay, for simplicity. Okay, for simplicity, I'll just give a brief idea about how you understand. Okay, material is crystalline or not. So normally, to understand whether the material is crystalline or not, we do X-ray diffraction of the material. For example, you take an X material, you don't know whether it's crystalline or amorphous. Okay, how you know that whether it's crystalline or amorphous? So for that, you have to expose the material to the X-rays. Okay, so you can see the X-rays, they come and they hit the atoms. There are layers of atoms, one layer, second layer, third layer, fourth layer, and D is the interplanar spacing, the spacing between two consecutive layers of atom. Here the incident ray come, they diffract. Okay, this is ray 1, this is ray 2. Okay, and after some time, after the travel few distance, there will be a path difference, or there will be some interference. They will meet somewhere. So we need to calibrate that path difference, and the two gentlemen known as Sir Lawrence Bragg, Sir William Henry Bragg. So this gentleman, this William Bragg, is the father, and this Lawrence Bragg is the son. So they are the two British physicists. Okay, and they have contributed a lot towards the crystal structure determination using X-ray, and in fact they won the Nobel Prize in the year of 1915. Okay, interestingly, this X-ray was invented by a Rontgen. Okay, but the gentleman didn't patented that technology, this X-ray technology. Okay, that's why there is lots of development took place in this area, and these two physicists, they carried on the experiment and they came up with a very interesting, which is the backbone of today's modern material characterization. So you can see, if I do X-ray dissection of any unknown material, so I will see the lines. You can see these lines are there. These lines. Okay. these three lines corresponding to amorphous, polycrystalline, single crystalline. What is the difference? The difference is that the way this black lines appears, okay, the way the black lines appear, they are the blueprints of the material, the structure of the materials. Like your skeleton is the blueprint. Okay, how a human skeleton is different, how a human body is different from an animal body and an aquatic animal like fish. So they all three are different, but all three are different. Based on what? Their physical structure. How I know the how will I understand the physical structure? When I see the X-ray diffraction pattern of all the materials like amorphous, you can see there is a wavy nature of this. You can see there is, but you can see for a single crystal, this peaks is very sharp peaks at particular angle. Okay, it is called Bragg's angle. You can see 2 theta. So these are called Bragg's angle. So at Bragg's angle uh, there will be constructive interference. You can see when constructive interference will happen, this equation will holds valid. N lambda equal 2d sine theta, where n is the order of reflection, lambda is the wavelength of the X-ray, your d is the interplanar spacing, sine theta. Theta is a Bragg's angle. Okay, so at a Bragg's angle for single crystal, you will have a very intense peak, very intense peak. You can see very intense peak. But when there is a polycrystallinity, the peaks, the sharp peaks will start broadening. The broadening of peaks will start. Okay, when the moment the polycrystalline metal will become amorphous, you will not see any intense peak. There will be huge broadening. Okay, that is the measure, okay, with which you can distinguish a material whether it's single crystal, polycrystal, or amorphous. It's a basic understanding I've given. There are lots of analysis there. Okay, so based on this, lots of modern material characterization techniques, you can see electron diffraction. Okay, your EBST, electron backscatter diffraction. They are all based on this X-ray diffraction technology. If you are interested, we will be discussing on this briefly in some other lecture. So now we'll move on to the timeline for the evolution of material science. Okay, I mean, there is a evolution like human evolution. Okay, there is a evolution of materials. In unlike your human evolution, earlier we were not as developed as today. So people say that our forefathers are monkeys. We have evolved from the monkeys. So the monkeys, the thought process of monkeys were not as equal to a thought process of human, even though we have a same gene. So we have evolved. There is evolution. So similarly, here also we have evolution. We from in the 10,000 BC, where in the Stone Age, all the articles have been used of stones. Okay, then now we slowly moved to Bronze Age. Okay, next we went to Iron Age. Okay, next we went to age of steel. Okay, next polymers, silicon. Okay, so we evolved through. Okay, we evolved, and we can see in case of metals there was the evolution. Okay, what was the evolution? Like gold in the ancient time, people were not aware of their other uses. Like they were only using gold as an ornament, luxury items. Okay, but you can see nowadays for electronic devices, gold is one of the major components. Okay, the element is same, but the application has changed the complete exposure of the metal. Okay. Even similarly, the iron was invented somewhere in the 1000. Okay, and it took around another 900 years. Okay, 900 to 800 years to understand that steel can be manufactured by adding carbon into iron. Okay, so steel has a distinct feature. Pure iron and steel, they are different. Okay, no doubt they have same elemental composition, but the properties of steel. Steel is nothing but an alloy of iron and carbon. So when you add carbon to iron, okay, the properties will change. You'll get the superior properties. Similarly, you can see the stainless steel. The evolution of the steel has given us the rust-free steel. Okay, so that is the evolution of steel. We invented iron, then we invented steel, then we invented stainless steel. So that is the evolution process. Okay, so now somewhere in 1960 there was a major evolution takes place with the invention of super alloy. Okay, super alloy is nothing but the nickel based alloys. Those are used for high temperature application, aircraft turbine blade manufacturing. Normally the melting point of steel is somewhere around 1500 degrees centigrade, but you can't use steel in aircraft gas turbine, they will melt. So we need superior alloys. Those are having not only a high melting point, but the ability to deform the material should be very, very superior compared to steel. That is nothing but super alloys can give you the characteristic of high temperature resistance alloy. Next, you can see this polymers, composites, ceramics. They have been using in the ancient time also. They've been using in ancient time, and there is a uniform evolution taking place, and you can see this in case of polymer, the invention of rubber, bakelite, nylon, PE, okay, acrylics, the sophisticated polymers, okay. And then the composite manufacturing started. Then we went to the composite. Okay, composite are nothing but the combination of two or more element in a systematic arrangement. Okay, so plywood is a classic example of a composite. Okay, where we are putting layers of woods, and we are giving us a certain arrangement so that wood can be the strength of wood can be increased. Okay, and there is a evolution takes place, and we nowadays we are having glass reinforced polymer matrix composite. Okay, Kevlar matrix composite. Okay, Kevlar is a polymer composite whose strength is 5 times more than steel wires. Okay, they're used for bulletproof jackets, preparation of bulletproof jackets. Okay, ceramics. Okay, ceramics. Earlier we were using only potteries. Okay, and now the ceramics are being used in spacecraft, space aircraft applications. I'll show you a case study where how important is the use of ceramic. Okay, so we'll come to the without periodic table, metal science is incomplete. So this is a periodic table where the entire element series has been categorized into 3 different parts. One is metals, another is metalloid, and another is non-metals. You can see the colors. Okay, the color difference. The blue color is being categorized metal, and the yellow color is non-metals. The green one is metalloids. Okay, I think you have studied in the 12th, but here I would like to mention important thing that those are necessary, that the metallic character, okay, metallic character will decrease from the diagonal corner, right diagonal corner to left lower diagonal corner. In this direction here, metallic character of the elements will decrease, and the non-metallic character will increase in from this direction. This is vice versa. Okay. Similarly, ionization energy, electron affinity, atomic radii. If you come from top to bottom, the atomic radii decreases. From from left to right, the electronegativity increases. Similarly, electronegativity increases from bottom to top. Okay, so why I'm mentioning all this electron affinity, electron negativity, we have all studied in 12th. Okay, The use is that they play a key role while forming bonds between atoms. Okay, there are certain criteria which we'll be discussing. Okay, where we'll be discussing the role of all this characteristic: electron affinity, ionization energy, okay, electronegativity. So these all the elements are arranged in such a way that it's beautiful, in a very beautiful way. So this periodic table was invented by a Russian metallurgist, Mentleev. Okay, yeah. So that guy has beautifully arranged all the materials, and so that we can represent in a uniform way that how electronegativity is increasing uniformly. There is no confusion in it. Okay, so you can keep it in your mind how things are changing in a predictable, the metallic character, the electronegativity. Coming to the next point, yeah. So it will be very interesting to discuss some historical blunders that took place, okay, in the past. That is a living example of failure of material. So one is your space shuttle Columbia disaster that took place in 2003. Okay, in 2003, the space shuttle, the famous astronaut Kalpana Chawla, she died when the space shuttle was re-entering the orbit of Earth. Okay, so what happened exactly? So there is a fuel tank. You can see this fuel tank of this uh, spacecraft. Okay, and you can see this is the image of the spacecraft just before it broke into pieces. So there are some debris coming out of the left wing. Okay, the left wing. So that is the brief investigation suggests that this block, you can see that this block is protecting the fuel tank of the Columbia spacecraft. So while refilling, what happens? Some maintenance work just before the takeoff of the spacecraft, a big chunk of this ceramic foam block. This is the ceramic foam block. It came out. Okay, and it is such an unfortunate event. So because of this problem, okay, the ceramic block it fell from this fuel tank, and you can see there is a gap. Because of this, what happened? So when this spacecraft was re-entering the orbit, it was completely in continuous contact with the atmosphere, and because of the friction with the atmosphere, the temperature of the spacecraft, the outer temperature, shoot up to 600 degrees centigrade. Okay, the purpose for which this ceramic block was insulating, okay, this fuel tank hose, so that during this re-entering, okay, the temperature will definitely increase, and the the reason why this foam blocks were given to protect the fuel tank from rising this temperature to 600. It will keep the temperature below 600 or 1500. So because of this high rise, there is a explosion happened and it broke into pieces. If that accident that removed this chunk of foam block from this fuel tank would not happen, then this disaster could not happen. So you can see that is such a essential element, okay, functional element that is made of ceramic, okay, which can lead to a disastrous space mission. Okay, so this is one example of material failure. Okay, next is the best of the best, Titanic ship, 1912. Okay, so generally what happened? So you can see this is the ship hull. Okay, when this ship hull it collided with a iceberg. Okay, so what happened? The compartment, the front compartment of the ship, they filled with water. Okay, and this leak was not, it was so big that this ship was broke into two pieces from the middle. Okay, that is another design failure that can be discussed later. But the main important failure is that you can see the ship hull, okay, were prepared using sheets, okay, and they joined using rivets. You can see the rivets are permanent joints, okay. So these rivets, they're generally made of steel, okay. So the regular rivets, they contain around 2% of slag. Slag is a byproduct of steel, okay, which generally found in steel because it cannot be removed. It is very difficult to remove slag. Normally, we remove almost 90 to 95% of the slag, but some slag remains, and that makes the steel weak. So the steel, which were the rivets, those are made of steel that those are used in this Titanic ship, were found to be 9%. The slag percentage was very high. Okay, and such a high slag, what happened at the time the Atlantic Ocean, the temperature, night temperature was in the negative. So because of that very low temperature, the rivets, they failed, okay, catastrophically. Normally, what happens? Steel is a ductile material. Okay, they have a very good elongation. Okay. Even if you apply a shock load, they will not fail catastrophically. They will not break into pieces. So when the temperature will go very down, very low, then they will act like a brittle materials. Brittle and ductile we'll discuss, okay, later. So this was the blunder. This is because of this faulty material. Okay, the entire ship, okay, is drowned and wrecked havoc into pieces. Okay, if this thing could have been, if the Titanic could have been built in 21st century, okay, then the scenario would have been different, because Titanic was not a small ship. It's one of the largest ships at that time, even all time. Okay, so these are the material. Some blunders happened in the past. Okay, now coming to the application of some advanced material. Okay, such as the advanced material like, yeah, shape memory alloy. Okay, actually my expertise in shape memory alloy, so I'd like to talk more about shape memory alloys. It's a very interesting alloy, and yeah, so you can see one wire made of nickel titanium. Okay, so this guy, what he has done, he has bent that wire, okay, will deformed very drastically, and he is just holding it. So now so normally what happens, if you release any normal wire, steel wire or copper wire, the general tendency is that it will be remain like this in coiled form, okay, because it is deformed already. Okay, but in case of this shape memory alloy, you can see the shape recovery will take place. Okay, so the moment when this guy will release, you can see it will become straightened. Okay, the strain recovery is much higher compared to any other material. Okay, that's why it is being. Now this guy, what he will do, he will take this wire, and it will try to keep it in the hand, and yeah, you can see the shape recovery taking place, because the deformation is taking place at a low temperature, but when we heat it, the complete recovery takes place. So that is called thermoelasticity. Okay, you can see, yeah, so from cold water he took and he kept it in his hand, which is around 30 degree, and because of this temperature difference, it recovers its complete shape. Okay. Now there is one more example. Okay, where actually I prepared these wires. So we have to memorize the wires, and when you apply heat energy to a deformed straight wire, okay, it will try to recover its original shape. You can see this alphabet R. It was memorized in the shape. Okay, but when whatever shape you give, and the moment when you heat it, it will come back to its original position. So that is the beauty of this material, and we'll be discussing if you are interested. So next is the application of this shape memory alloy by an aircraft that is called F-18, designed by NASA. Okay, so you can see this is the shape memory alloy. Okay, they've used for this adaptive spring wing design. Okay, the same thing which I discussed in the past. So there is, you can see this is the wing, this is the adaptive wing. Okay, and this wing is joined by using a hinge. Okay, in the hinge you can see, yes, you can see this actuating mechanism that is being carried out by using nickel titanium springs. Okay, so this is the wing. Okay, and this, yeah, you can see this is the shape memory alloy springs. Okay, wires. Okay, these wires are used. Okay, so this is the lab of NASA, and this is the design of the adaptive wing, in which this SMA wires will be inserted. Okay, and when you heat those wires, okay, you see they're testing these wings. Okay, they're applying they're monitoring this angular twist with torque. Okay, as we heat the SMA wires, they start exerting force, and the force will convert to torque. Okay, and this they have tried with a more broad range of angle of twist. Okay, in earlier case it was 0 to 45, and now here minus 45 to 45. Okay, so okay, uh, let's discuss one more application that is called heat engine using SMA wires. You can see this is the heat engine. Okay, normally it has two wheels. One is bigger wheel and is lower wheel, and part of the wire is being dipped into hot water. There is no other way of rotating mechanism. When the portion of the hot wire will come in contact with the water, it will try to recover its shape, and during the shape recovery process, it will generate a torque, okay, around the wheels, and the wheels will rotate. Now you can see the video how this heat engine works. You can see the upper wheel is rotating, and that is being connected by using this is a nickel titanium shape memory alloy wire. Okay, and this lower pulley is dipped into the hot water. Okay, because of this energy transfer, okay, this engine is running, the power is being generated, the heat energy being transferred to rotational energy, that is a conservation of energy. Okay, and it is being substituted by this nickel titanium wire. So these are the some beautiful and nice application of shape memory alloy. Okay, now let's have a look on the evolution of materials in sports. Okay. In sports, how material played a key role. Okay, that let's take an example of tennis sports. Okay, so here you can see the first tennis racket that was made in the year of 1870. Okay, and this was the same. It was made of wood. Okay, and some fiber thread they have been weaving around it, and it just look like this shape. Okay, now after a decade, you can see there is a slight modification in the design. Okay, but still they've been using wood as the frame. Okay, and just come to the design somewhere in 1920. You can see further modification in design. Until 1950, they were using wood for tennis rackets. Now, just go to this evolution of material slide. Uh, yeah. So the preparation of alloy steel started somewhere in the 1900, in the year of 1900. Okay, and the aluminum alloys also came somewhere in the 1940 to 1960 region. Okay, light alloys, you can see this year 1940. So after that, now coming back to that slide, somewhere in 1976 they made their first tennis racket using steel frame. Okay. Steel frame. Then after a decade, they again jumped to the aluminum because it was light and dense. Okay. But now you see in the year of 2017, they're using a graphene composite, a very lightweight composite, okay, for the manufacturing of this tennis racket. No one knows in 2050 there is something else they will use it. Okay. So this is the evolution of materials in sport, okay, from the first racket to the most advanced racket. This is how the development took place. Okay. So I think this is sufficient for the introductory session, and I would like to take up some quiz for you. Okay. So let's start the quiz one. Okay. So the first question is, out of below mentioned options, which one belongs to advanced engineering material? You can see the options are alloys, metallic matrix composite, okay, piezoelectric materials, RCC steel. So to answer this question, so let's jump back to the advanced engineering material slide. Yeah, here is the advanced engineering material slide, and you can see the piezoelectric material that comes under the smart material, which comes under the advanced engineering material. So we've got our answer. Let's get back to the question. Yes, so the answer is C, the piezoelectric material. So let's jump back again, the next question. So we need to opt out the true statement from the below mentioned option for predictable. Okay, so there are so many statements that the atomic radii of the elements increases from top to bottom. The electronegativity increases from left to right. Okay. And the electronegativity increases from right to left. Electronegativity increases from left to right. Electronegativity increases from top to bottom. So let's go back to the periodic table. Yeah. Yeah. So we have options where atomic radii, electronegativity, electron affinity was there. So the atomic radii increases from decreases from top to bottom, but in the option, you can see in the option, the atomic radii increases from top to bottom. So that is a false statement. Now coming back to the electronegativity, okay, the correct statement is that the electronegativity increases from left to right. Left to right. Okay, let's find whether it is there. The statement. Yeah, the electronegativity, the true statement is the electronegativity increases from left to right. Okay. And the other two statements are, I think, false. So let's have a check. Electron affinity increases from right to left. Electron affinity increases from electron affinity increases from left to right. Okay, so that means it's a false statement. Okay, and electron affinity also increases from bottom to top, not top to bottom. So these two are false statements. Next, coming back to the next question. So when was the birth of superalloys? Which year? So this answer can be found out from the evolution of materials. Yeah, see. Yeah, you have cast iron, you have steel, you have alloys, light alloys, 1940, super alloys, 1960. Yes. So in the year of 1960, the super alloys came into picture. So hopefully the answer should be, yeah, 1960. The what else for alloy? So the option is A. Coming back to the fourth question, the foam block that was protecting the fuel tank of Space Shuttle Columbia was made up of dash. Whether it's a polymer, composite material, steel, alloy, ceramic. Polymer, very difficult. Composite material, maybe steel, aluminum alloy, ceramic. Let's get back to the slide. Get back to the slide. Space Shuttle Columbia, they used this ceramic foam block for the preparation of this tank insulation. So I think it's ceramic. The answer is ceramic. Let's go once again. Yeah, it's ceramic. It's the answer E. Okay, so the next problem, the steel rivets used to join the seats used in the ship hull had how much percentage of slag in it? So the steel, for the production of steel, there will be some amount of slag, but for the case of Titanic ship, I think the ship hull, okay, contain how much? Let's have a look. Yeah. So the answer is normally we find 2%, but for the Titanic ship, the slag percentage was 9%. So let's check the answer. Yes, 9% is the slag percentage for the ship hull. So with this, I would like to complete my presentation, my talk, my lecture. I hope you like the lecture. Please comment if any improvement can be done on this. I would like to definitely like to take on the suggestions. Thank you.